we consider a one-dimensional case of a particle. Say any particle is moving only in the x direction. Okay, so as it is moving, it is covering some distance, so it will have an x coordinate, and since it is moving with some velocity, it has a mass, it will have a momentum. So as the particle is moving, we can note its displacement, that is position, and its momentum. Okay, if you are plotting such the movement of particle in a plot where one of the axis is the x-axis and the other axis is the, instead of y, px axis, okay, then such a plot is called the phase space. Okay, and in this you will have the motion of the particle going. So let us say if I consider one particular point like this, then this x position corresponds to this momentum, this x position corresponds to this momentum. So basically from this we can find the information from each point on this line. We can find the information regarding the state or the condition of the particle. Okay, so now this is the phase space, but phase space representation is different for different theories. So for example, if you are considering this system in a classical sense, then each point on this curve, okay, is a particular state of particle. So for here also I'll get x and px, here also there will be a x and px, here also there is x px, here also there is x px, here also there is x and px. So at each point I'll get the information about the position and the momentum of the particle. Okay, so this kind of understanding is true and valid when the picture that you are considering is a classical picture, or when you are talking about classical mechanics. But if your particle is moving and you are considering the picture from a point of view of quantum mechanics, in that case I cannot consider a small point. Okay, because if I consider a point, then my x is fixed. If my x is fixed, then what will happen? Heisenberg's principle says that if x is fixed, then px will not be fixed. Okay, we know that by Heisenberg's uncertainty principle, delta x into delta px should be greater than or equal to h. Okay, so now if my x is fixed, that means my change in x is very small. If my change in x is very small, to have h, my change in delta p, okay, must be very large. Okay, so if I know delta x, then my delta p is uncertain, and if I know delta p, then my delta x is uncertain. Okay, so if we if we can take careful measurements such that delta p into delta x are almost equal to h, okay, then what happens? That the picture will become something like this. Instead of a point, there will be a one square block. Okay, there will be one square block which will represent the state of the particle instead of a point, which was in classical mechanics. Okay, why? Because delta x, which is for this point x0, okay, shows the uncertainty in the position of x, and for px0, the delta p will show the uncertainty in the position of momentum, angular momentum. So this product should be equal to delta x into delta p should be equal to h. Okay, now since h is a non-zero value, okay, that means it will have some area. So we are showing it by a small cell. Okay, so that is why, because of the quantum picture and the Heisenberg's uncertainty principle, instead of a point, you will have to consider a rectangle or a cell to describe the state of the particle. So for a particle of having approximate value of x0, okay, the delta x into delta p will give you this whole region. Actually, this whole region, okay, it shows what? It shows the state of the particle. It means particle can be having any of these values, delta p and delta x. Okay, so similarly for y also that will be happening, and similarly for z. Okay. So basically what happens is this is the current scenario. So when we, now what happens is that, okay, the smallest, so h is the volume or the area of a particular single state. Now if I consider p into x, so this is a bigger area. So in this bigger area, how many h can be added? Simply divide p into x by h. If I p into x by h, if I divide it, then I will get the number of h particles I can put inside this box, okay, or in this region. So that means now what is h? H represents state of the particle. So that means that p into x by h cut by h will give me the number of states in this particular region. We are interested in actually finding the number of states. So this p into x by h will give me the number of states in this particular region. Now instead of h, I am interested in having h cut, so I will multiply and divide by 2 pi, so I will get 2 pi h cut. Okay. Similarly, when you are considering the case for py and y, pz and z, again I will get expression ny will be py by h cut, nz will be pz by h cut. Okay. Since this is one dimension, this is one dimension, this is one dimension, when all three are combined, you will get the picture of a particle, single particle. Okay, you will get a picture of a single particle in 3 dimensions. That is why your equation will be written by n1, that is for one particle only. The volume will, instead of 2 pi h cut, it will be 2 pi h cut whole raised to cube. And now px into py into pz, that is integral of d cube x, then p and p, 3p will give you d cube p. Okay, so basically in 3 dimension space, your phase space will have 6 variables: x, y, z, px, py and pz. So that is why the integral is over d cube x and d cube p. Okay, so this is what we have covered till now. Okay, is there any query with regard to this that we have covered? Anybody has any doubts?
સર આ જે ડેન્સિટી સ્ટેટ ફેક્ટર છે એનામાં એનર્જી વધશે તો જો ડીઈ વધશે તો ડીએન ની સંખ્યા પણ વધશે ને પોસિબલ સ્ટેટ?
જરૂરી નથી, it depends on the system. Sometimes DE increase કરે DN increase થાય, sometimes DE increase કરે DN decrease થાય. It is just a formula. આમાં કોઈ રિલેશન નથી મેન્શન કરતું, બરોબર છે? એ રિલેશન જે છે it will depend on system. કઈ ટાઈપની સિસ્ટમ છે એના પ્રમાણે એ ફોર્મ્યુલા બનાવવાનો આન્સર બદલાશે. આ એક શું કહે જનરલ એક્સપ્રેશન છે, જેમ F is equal to m into a, બરોબર છે? ફોર્સ ઇઝ માસ ઇન્ટુ એક્સેલરેશન છે, એવી વાત કરી દીધી એમ કે rho of E is equal to dn by de. ડિપેન્ડ ઓન સિસ્ટમ n નો એક ફોર્મ્યુલા તમારે ક્રિએટ થશે અને પછી તમે E થી ડિફરન્શિએટ કરો એટલે તમને ખબર પડે કે rho E નો ફોર્મ કેવો છે. ઓકે
ઓકે સર.
હા, okay, so in that case I'll assume that everybody has understood it. Okay, then I'll go a bit further. Now till now the volume was what? P into x, or P into x, then P into y into P into z. So x, y, z whole cube is formed. Okay, now in this cube, if I, instead of saying px and py, if I make the volume unit, so if I the whole value of the whole volume is 1, in that case if I take the integral of d cube x, it will be 1, because what is it? Unit volume. Now d cube x is what? Volume in x, y and z. Okay, so that is unity. So integral of 1, so what happens is one term from this expression goes away. Okay, so this becomes 1. Okay, so what happens is your expression becomes n1 is equal to 1 by 2 pi h cut whole cube integral of d cube p. Okay, so now what is happening is, now that your integration is with respect to momentum only. Okay, so basically if you want to consider compute the density of states for one particle, then the formula is rho 1 of E, because here 1 is used to indicate that it is only for one particle. Okay, so for one particle it will be dn1, because n1 is this formula, by dE. Now substitute the value of n1 here. So what I will get? I will get 1 by 2 pi h cut. Okay, because it is constant, will come out. Now d by dE is here, and then there is the integral of d cube p. Okay, now in our elementary electrodynamics and electromagnetics, or even electrostatics, we have considered the expression for volume. Okay, so when your volume is d cube p, if you expand it in 3 dimensions, you can write it in the form of that d cube p can be written like this. Okay, so 2 dimensions are mentioned, p square. Okay, and the 3rd dimension is taken as a small variable, and again one more thing is added, d omega. D omega represents the angle in space. Okay, generally you are having an angle between 2 lines only, but since this is a 3-dimensional system, the angle is your solid angle, so it is an angle in space, 3 dimension. Okay, so it is called solid angle. So what we'll get, d omega is the solid angle element corresponding to the emitted particle. Okay, so basically what happens is the momentum variable p square and dp, so changing momentum is mentioned here. Okay, and then when it is momentum means this particle is emitted, in what direction it is emitted, that is taken care of by the solid angle element. Okay, so it is basically considered the whole 3-dimensional space by this expression. Now, okay, now if your particle is emitted, okay, then the energy of that particle can be given by this formula, E square is equal to P square C square plus M0 square C raised to 4. Okay, so this is the expression from relativity. If you all remember, then we have an expression, E square is equal to P square C square plus M0 square C raised to 4. Okay, so now I will give you 5 minutes. Okay, differentiate this expression, E square is equal to P square C square and M0 square C raised to 4, and give me the next expression. Okay, if you cannot find d by dE, then just find dE. Find the formula or the expression for dE. Okay, I'll give you 5 seconds, almost 5 minutes, and then we can discuss if anybody. So we'll obtain this expression, d by dE is equal to E by P square C square into d by dP. So what we'll do, we'll substitute it here. d by dE ની જગ્યાએ એને expression ને substitute કરીશું આપણે. Yes
સર આપણે જે p નું કરીએ તો એ 2p થશે, તેમાં જે 2 હતો એ કઈ ગયો?
બંને બાજુ સારે e માં 2p આવશે ને, છે ને. E square will give you twice E dE, and P square will give you twice P dP. So બંને બાજુ 2 cancel થઈ જશે.
Okay, સર થઈ ગયું.
Okay, so now what we'll do, d by dE નું replacement કરીશું. We'll replace d by dE by E P C square d by dP. Okay, here. So when you replace it here, you will get the form 1 by 2 pi h cut whole cube is there. Okay, P into E. Okay, niche no P che, the P that is below, and P square will cancel out, so 1 P is left, so you will get P into E. Okay, and C square is already below, so C square will be available. Then integral of d by dP will be there. Okay, integral of d by dP will be there, and then there is this integral and dP. So dP will cancel out, so only d omega is left. So what you will get? You will get an integral over d omega. Is everybody clear? Okay, maybe I can do something about it. So are you able to get it? So in this expression, I'll forget 1 by 2 pi h cut whole cube. I'll forget. I'll just use d by de. So d by de, instead of d by de, I'll write here capital E by into bracket
Okay, sir.
PC square. Okay, PC square. Assume that the 2 is above. Okay. Now there is the integral sign, so I'll just write integral into bracket p square. Okay. Into dp into d omega. Okay. So now what will happen is p is below and p is above, so p and p will cancel. This p and this p will cancel, so one p will go away. So what we'll get is, you will get only one p is left. So now there is E by c square p into dp omega. Okay. Now okay, when I substitute E by p square, there is d by dp is also there, so I have forgotten to write that. So here there will be d by dp also integral. Okay, so next step what will happen, dp and dp will cancel, dp here and dp here will cancel out, so I can remove this whole term here, and the whole dp here will also go away. So now the integral is with respect to p into d omega. Okay, so now since d omega is your variable, p becomes a constant, so p will come out, so you will get E into p by c square. Okay, so integral will be over d omega. Okay, so this is what you are getting. P1 means density of states for one particle is equal to 1 by 2 pi h cut whole cube Pe by c square integral of d omega. I hope it is clear to everybody. Now we'll go further. So when you are considering integral of d omega over all space in all directions. Okay, so for all momentum directions, when the transition to all final states is considered, integral of d omega is equal to 4 pi. Okay, when you are considering all dimensions, generally integral of d omega is equal to 4 pi. So density of states can be written simply as, instead of integral d omega, you can write as 4 pi. So substitute the value of 4 pi. So you will be able to cancel some of the terms here. So you will get an expression equal to rho 1 of E is equal to 1 by 2 pi square h cut cube rho E by c square. Okay. So is this clear to everybody?
Yes, sir.
Okay. So in that case, so basically this is what the density of states for single particle that we are considering. Okay. Now what is happening is, what in beta decay, what is the initial state and what is the final state, that we will talk about. The beta decay problem involves three particles. For example, if there is a proton, so if there is a neutron, it will give you a proton, electron and antineutrino. Okay. The initial state I corresponds to the neutron. Okay. So what happens is, initially you have a neutron, so that is the initial state, and the final state is what? The final state is we get a proton, electron and an antineutrino. Okay, so in the final state we have three particles, that is a proton, an electron and an antineutrino. Okay, so now here what happens was, the equation was for only one particle, but now we know that the final state has three particles, that is proton, electron and antineutrino. Therefore this equation must be considered for three particles only. So therefore we must extend the equation to three particles. So this is easy. For three particles, the momenta of the two particles can be can change independently. However, the conservation of momentum fixes the momentum of the third particle. Okay, so what it is saying here is that, okay, we know the law of conservation of momentum. So that is momentum before is equal to momentum afterwards. Okay, so initial momentum is equal to the final momentum. Okay, so initially it was whatever was there, that should be the result of final. So what happens is that the final momentum should be equal to the sum of the proton, electron and antineutrino. So all the three of them should have the, when they are added, you should get one fixed answer. Okay, so what does this imply? It means that if we know the two, the third is easily calculated. Okay, if we know the momentum of proton and electron, then we can easily calculate the momentum of antineutrino, or if we know the momentum of antineutrino and electron, we can calculate the momentum of proton, or if we know the momentum of proton and antineutrino, then the momentum of electron is easily calculated. Therefore, what they are saying is that the conservation of momentum fixes the momentum of the third particle. Means if you know the momentum of two particles, the momentum of the third particle is fixed. Okay, easily calculable. Therefore, what is required, even though it is a three particle system, only the information about two particles is sufficient for our case. That is, if P1 and P2, momentum of the two particles, are known, then the momentum of the third particle gets fixed by the relation. If you assume that initially the momentum is 0, then P1 plus P2 plus P3 is equal to 0 in the center of mass system. Okay, so basically we are now only needing information about two systems only. Okay, so that is why the number of states that can be crammed in the unit volume in phase space for three particles can be written as, now see, this is for one particle. Okay, now if there is another particle and one particle, okay, let us say this is the expression for one particle. Okay, now if you have three particles, then it will be n1, instead of it will be n1, it will be n3. Okay, n3 will have, when you consider n3, then your expression will be equal to n1 into n1 into n1, so it will be n3. Therefore 1 by 2 pi h cut cube d cube p, then it will again 1 by 2 pi h cut cube d cube p, again it will be 1 by 2 pi h cut cube into d cube p. This will be repeated 3 times. But since we have already mentioned that if you know the information of 2, the information of third is easily available, so your expression for n3 will consider only equations 2. So what you will get is 1 upon 2 pi h cut cube into 1 upon 2 pi h cut cube into d cube p1 into d cube p2 only. Okay, why? Because the information of a third particle is easily calculated if you have the information of two particles. Sorry, from this relation P1 plus P2 is available, then P3 can be easily found out. So there is no need to add integral for P3. Okay, that is why there is no calculation of P3 also involved. So there is only 2 pi h cut cube into 2 pi h cut cube twice. Okay, so for n3 the density of states will be equal to rho 3e, that is dn3 by de. Okay, so again we'll repeat the process that we have done for first particle. So it is 1 by 2 pi h cut cube d by de, d cube p1, d cube p2. Okay, so now this is your expression. We are not solving it right now, we have just kept it here. Now see, we have three particles, proton, electron and antineutrino. So which are the particles of interest, or whose momentum should we be calculating? So P1, P2, so we need to determine which is the particle 1 and which is particle 2 of our interest. So what is saying, now let us choose particle 1 to be the electron and particle 2 to be the antineutrino. Now why are they doing this like this? why is the proton ignored? Because the third particle is the final state is the recoiling nucleus, which is much more massive than either the electron or the antineutrino. See, in this expression, we are generally consider neutron gives proton plus electron and antineutrino. But normally this happens where? It happens in the nucleus. So the nucleus is very heavy. In this nucleus, one neutron will give you a proton and electron and antineutrino. The proton will stay in the nucleus only. Okay, so basically nucleus is much heavier than electron and antineutrino. So what happens is mostly its momentum is unchanged. Okay, so it's stationary. So the particles which are having the momentum, most of the momentum are electron and the neutrino. So it is better that we consider electron as the first particle and the antineutrino as the second particle whose information is available. The third particle, proton, which is inside the nucleus, so therefore the third particle can be the nucleus whose momentum can be easily known once we know the information about the electron and the antineutrino. So that is why here it is considered that the third particle in the final state is the recoiling nucleus, which is much more massive than either the electron and the antineutrino. So because of its major size, most of the energy is it does not carry energy much, because most of the momentum lies in its mass. Okay, so its velocity will be very small. On the contrary, because the electron and the antineutrino are light particles, they will carry out the major momentum. Okay. Now, one of the best examples to understand this kind of a situation is considering your mobile. Okay. Right now we are using smartphones, but before that we had feature phones, and generally at that time, initially when mobiles were launched, there was a period when Nokia phones were very much popular. Okay, I hope you remember that. Now, one of the fascinating ideas, the design details of Nokia phone was that whenever it fell down, it completely broke. All the parts became separate. So, why do you think such a design was made, that its parts can become easily separate? Because when the mobile falls from your hand, okay, it is falling to the ground with a certain momentum. Now, if it was a fixed rigid body, then once it touches the earth, the reaction from the earth will give back the same momentum back to the phone. Now, if it is a rigid body, then all the momentum will be given back to the complete phone. So what will happen? The phone will get damaged. But instead of that, if there are parts which can easily separate, then what will happen? When the mobile touches the earth, the energy that is reflected back, okay, it's taken away by the parts which can move away easily. Okay, so the small parts, or it breaks down, they will carry away most of the damage and they will fly away, whereas the body of the phone will remain intact. Okay, so basically this is where the principle of conservation of momentum is very much helpful. Okay, so basically this causes the damage to the phone to reduce, and most of the energy that is reflected back is carried away by the small parts which are thrown around. Okay, so here also what we are considering is that the mobile phone itself is a nucleus. So when it falls down or breaks, the small particles that are coming out can be considered as your electron and neutrino. So they will carry away most of the momentum of the system, whereas the phone will stay in the same position. So its momentum is generally zero, or it is very small. So basically instead of particle 1 and particle 2, we will use the label, instead of 1 we will use the label E for electron and nu for neutrino. So that is why our problem here, dqp1 and dqp2 will now be written as dqpe for electron and dqp nu bar for antineutrino. Okay, and now energy becomes energy max. Now what is this? This is the maximum energy that is available to the electron when the d beta decay takes place. That is why the differential is with respect to the maximum energy that is available to you. Okay. Now note that the Emax being the total energy of disintegration, it is incorporated into the equation. The objective is to know how the integral changes when the total energy is varied. Emax is varied. Okay. So that is why we are using Emax here, so that we know that when Emax changes, how much is the change in the system. Okay. Now, as we did in the case of the one dimension, okay, what we did is we instead of dqp, we wrote p square dp d omega. So here also it is p square pe square dpe d omega e. Now this omega is for electron only. Similarly, for antineutrino, p nu bar square dp nu bar square d omega mu bar. Okay, any queries, any doubts till now?
No, sir.
Okay. So basically whatever was we had done for the one particle case, we are now doing for the three particle case. Okay, just the labels are being changed. Okay, so d omega is the solid angle element in which the electrons are having the momentum between pe and pe plus dpe. Okay, similarly d omega nu bar is the solid angle element corresponding to the antineutrino. So whatever is here for the electron, the same is for the antineutrino. Okay. Now how to solve rho of E? Okay. Now let us look at the continuous spectra in figure, which is plotted on the y-axis. The number of beta particles emitted between range EE and EE plus DE. Okay. So what it is saying is that consider this figure. You have to consider any one of this figure if you consider. And what is saying that these are the energy of the electrons. Now information that is available is for this particular energy there are this many electrons. Okay, so let us say consider some small energy E and some small change in it DE. Okay, so let us say the energy ranges from 0.2 to 0.25. That kind of scenario you are considering. So when you consider that, therefore to calculate PE, E and also PE is kept constant. Okay, energy is constant. So what happens, the change only takes place in the DE part or DPE part. This implies that the terms concerning the electron remain unaffected by the differentiation with respect to total energy. Okay, so what is happening is the number of beta particles and between the energy range are being shown. Okay, so in order to find density of states, what we are interested in is not the energy change, it is the energy itself. So since the energy is not considered fixed, it's not considered variable here, E and momentum, energy and momentum are kept constant. Okay, so we'll highlight this part. So energy and momentum are kept constant. This implies that the terms concerning electron are almost constant by differentiation with respect to energy. So what happens is p square dpe and p nu square are constant. The only change when this will operate, it will operate only on what you say is dp nu bar square. Why is it doing so? Because in the graph we already have information regarding the electron. We have the information regarding the electron momentum, electron change in momentum, and electron angle also. Electron angle is not, no, that is variable, so it is direction is considered constant. But again, the antineutrino momentum information will also be available from electron momentum, so that is also considered constant here. So the only change variable which is affecting everything is dp nu bar by d Emax. Okay, so in this expression pe square, p nu bar square are constant, and then there is dpe which is considered as constant. So basically all terms related to electrons are generally kept constant. They are not considered because the spectrum information is about electron mostly. Okay, so now Emax. Now what is Emax? Emax is the maximum energy available when the decay takes place. Now when the decay takes place, you will get a nucleus, you will get an electron, and you will get an antineutrino. But as we mentioned before, that the recoil energy of the nucleus is very small. Okay, so we can neglect it. Okay, so if we neglect the recoil energy of the daughter nucleus, then what we can do is we can write that maximum energy, that is Emax, is equal to EE and E nu bar. That is, the electron and the antineutrino have the access to the total energy Emax. Okay, the electron, the proton, or the nucleus generally does not take away the energy. Okay, so now if we assume again that the rest mass of the neutrino is 0, in that case, if the rest mass is 0, in that case what will happen? Based on Einstein's relation, based on this relation, if the rest mass is 0, then m0 is 0. So what you will get, E square is equal to P square C square, or E is equal to P into C. So in case of neutrino, what we will get? E nu bar is equal to C P nu bar. Okay, clear everybody? Okay, everybody is being clear, or is there any, do I need to repeat some points? Our time is about to end, so I will be, yes.
सर लास्ट में आपने बोला ना, वो समझ में नहीं, लास्ट वाली इक्वेशन।
लास्ट में कौन सा वाला? ये वाला, ये Emax वाला या उसके बाद वाला?
हाँ ये वाला कसर है ना आपका सर, वो
ये E nu bar is equal to C P nu bar.
यस सर।
ओके, ये तो बेसिकली हमने जो इनिशियल इक्वेशन लिया था ना, यहाँ पे मैंने बताया, ये जो हमारा इक्वेशन था एनर्जी वाला, ठीक है, ये तुम्हारा जो इक्वेशन है, एनर्जी स्क्वायर इज इक्वल टू पी स्क्वायर सी स्क्वायर प्लस m0 स्क्वायर सी रेज़ टू 4 है। ओके, इस एक्सप्रेशन में अगर हम न्यूट्रिनो कंसीडर करते हैं तो क्या हो जाएगा? हम समझते हैं कि न्यूट्रिनो का मास 0 है, तो m0 विल बिकम 0, तो बचा कि कौन सा टर्म बचेगा? ई स्क्वायर विल बी इक्वल टू पी स्क्वायर सी स्क्वायर। ठीक है, अब यानी स्क्वायर रूट कर दो तो ई इज इक्वल टू पी इंटू सी बन जाएगा। ओके, अब क्योंकि न्यूट्रिनो है इसलिए ई की जगह पे ई न्यू बार लिखा है और पी की जगह पी न्यू बार लिखा हुआ है। ठीक है, इससे तुम्हें ये तुम्हें ये एक्सप्रेशन तभी मिलेगा जब रेस्ट मास ऑफ द न्यूट्रिनो इज 0, ये तुम कंसीडर करते हो। ठीक है, तो अभी तुम क्या कर सकते हो कि Emax मिल गया, Emax से तुम्हें क्या मिलता है? ई प्लस ई न्यू बार मिल रहा है। ठीक है, अब ई न्यू बार की वैल्यू हमें मिल रही है सी पी न्यू बार। ओके, तो अगर ई को कांस्टेंट ले ले, ठीक है, इन दैट केस हमें क्या मिल सकता है? डी पी न्यू बार बाई डी पी ई इज इक्वल टू, ठीक है, हमें क्या फाइंड करना है? डी पी न्यू, हमें ये टर्म ढूंढना है, हमें ये टर्म फाइंड करना है, डी पी न्यू बार बाई डी ई मैक्स, ये फाइंड हमें करना है। तो हम क्या करेंगे? बेसिकली सी पी न्यू बार के लिए हमने रिलेशन ढूंढ लिया है, पी न्यू बार इज इक्वल टू ई न्यू बाई सी होगा, तो यहाँ पे क्या सीखा? 1/1/c आ जाएगा, और क्या आएगा? डी ई न्यू बार बाई डी ई मैक्स है। अब डी ई न्यू बार को हम कैसे लिख सकते हैं? इज इक्वल टू ई मैक्स माइनस ई लिख सकते हैं, तो डी बाई डी ई मैक्स माइनस ई। ठीक है, और यहाँ पे क्या किया हमने? ले लिया कि ई इज कांस्टेंट, एज्यूम कर लिया हमने। अगर ई को हम कांस्टेंट लेते हैं, इसका मतलब क्या है कि जब ई मैक्स से तो डिफरेंशिएट करेंगे तो इट विल गिव यू 0, तो क्या मिलेगा, DE max by DE max आएगा, तो ये 1 बन जाएगा। ओके, और फिर दूसरा टर्म क्या आएगा, DEE by DE max, बट EE is taken as constant, तो वो टर्म 0 हो जाएगा। सो व्हाट विल गेट इज 1 by C, यानी ये क्या बोल रहा है कि इस टर्म का वैल्यू कितना है, 1 by C है ओनली। सो व्हाट यू विल गेट इज रो ऑफ ई, यहाँ पे रो 3 लिखना चाहिए था लेकिन रो ऑफ ई, तो 1 by 2 pi h कट 6 इंटू C, फिर PE स्क्वायर P न्यू स्क्वायर DPE इंटीग्रल D ओमेगा E D ओमेगा न्यू बार। ओके, अगेन यहाँ पे P न्यू बार की जगह पे तुम E न्यू स्क्वायर बाई C स्क्वायर डाल सकते हो, तो और E न्यू इज इक्वल टू E मैक्स माइनस EE, यानी हमने सारा एक्सप्रेशन है वो इलेक्ट्रॉन की एनर्जी के फॉर्म में और E मैक्स के फॉर्म में लिख दिया है। तो हमें क्या मिलेगा बेसिकली कि डेंसिटी ऑफ स्टेट्स इज इक्वल टू, यहाँ पे C की जगह पे ये P न्यू बार था, तो E न्यूज बाय C स्क्वायर था, C स्क्वायर इंटू C विल गिव C क्यूब। ठीक है, PE स्क्वायर है वो तो रहेगा, P न्यू बार में क्या आएगा, E मैक्स माइनस EE होल स्क्वायर, E मैक्स माइनस EE होल स्क्वायर DPE D ओमेगा E इंटू D ओमेगा न्यू बार। तो इतना इतना समझ में आ गया?
यस सर।
यस सर।
ओके, ठीक है, अभी तो आई थिंक मैं इसको यहाँ पे थोड़ा बहुत स्टॉप करता हूँ, क्योंकि बेसिकली हमें डेंसिटी ऑफ स्टेट्स का जो एक्सप्रेशन चाहिए था वो हमें मिल गया है। सो व्हाट विल डू इज, ये एक्सप्रेशन है विल सब्स्टिट्यूट इन द इक्वेशन ऑफ ट्रांजिशन प्रोबेबिलिटी, तो वहाँ ये यहाँ पे हम सब्स्टिट्यूट करेंगे, ये यहाँ पे जाएगा। ठीक है, तो बेसिकली दिस एक्सप्रेशन पूरा यहाँ पे ट्रांसफर होगा। ओके, तो वही उसने किया है, यहाँ पे सब्स्टिट्यूट कर दिया है और पूरा एक्सप्रेशन यहाँ पे लिखा हुआ है। ओके, सो आई विल स्टॉप हियर। कोई क्वेरी है तो प्लीज बताइए, क्योंकि नेक्स्ट 2-3 स्टेप्स ही हैं और कुछ है नहीं, लेकिन आई थिंक इट्स बेटर कि नेक्स्ट टाइम मैं थोड़ा बहुत फिर से इसको रिवाइज करूं और हम आगे बढ़ें, ताकि आई अगेन नेक्स्ट लेक्चर इज ऑन सैटरडे, सो टिल दैट टाइम ऑल ऑफ यू कैन go through this topic, and maybe if you have some queries or doubts then you can ask me.
सर बेसिकली पूछा है तो 14 मार्क्स में पूछा है आपको क्वेश्चन।
हाँ, तो basically it will be asked for 14 marks only, but what you can do is you can divide it into 2 parts. One is that obtain the expression of density of states for 3 particles. Okay, તો અહીંયા 6 સુધી અહીંયા આવવું પડે, બરાબર છે, અને in other cases obtain the expression for single particle. તો પેલું જે ઇનિશિયલી હતું ત્યાં સુધી ડિરાઈવ કરવાનું રહે. ઓકે, આ જે કેસ છે, લેટ અસ थिंक, આ જે એક્સપ્રેશન છે તમારા અત્યારે, this is an expression for 3 particle system, બરાબર, electron, proton and antineutrino. But if I say કે find the density of states for single particle system, okay, then your problem is still here only. Okay, so this can be 7 marks question.
Okay.
આટલું છે 7 marks પૂછી લેવા કે write the expression for transition probability and then derive the density of states for single particle. Then you can just write till here, here till here you can write and it is done. But if you say that for 3 particle problem, then you have to go and do all this also. Then it is a 14 mark question. Again, it will not stop here. I think mostly it will be this, all these things are also involved, so we'll cover them once you get a bit of a grip on all these things. Okay, so it is still large. We have to find the Curie function also. Okay, so we'll stop here. If you have any doubts you can just ask me. Okay, and we'll continue on Saturday. So at that time you can discuss whatever queries you have in the initial part, and then we'll finish off with this topic of beta decay. Okay. Now any other doubts or questions, queries?